I forgot to start my video. So I don't know when I stopped it, but I think I stopped it here. So this is a function. I made a mistake. I wrote sorry and I differentiated. I just started a new video. Sorry, I didn't get the chance to record this, but the sorry stays. Sorry. Okay, now it's running. I want to define three functions. And if you remember, we had a revenue equals profit minus cost. So basically we have, so profit, I meant to write, is the revenue minus the cost function. That's what I wanted. So as we know, these are the, we don't have to write it twice. I just wanted to start with the profit. So as we know, the profit equals the difference between revenue and cost. Now we also have something called average cost function. That is C of x divided by the number of units we manufacture. This is the so-called average cost. We're not talking about the average rate of change. This is a totally new function. The function is called average cost. That's the title. We also have something called average revenue. Which is the same thing, meaning it's the revenue divided by the number of units we manufacture and hopefully sell. Okay, the same thing for the profit. The average profit is a new function. We have never seen this function, these three functions before. Of course, it's the profit divided by the number of units manufactured and sold. Now, I'd like to look at a word problem. Why is this important now? Because when we want to differentiate, if we want to find the rate of change of the average cost, we're going to differentiate a ratio. Maybe not. Maybe we can simplify it. If we're asked to find the rate of change of the average revenue, we're going to differentiate this function, which is a ratio, and so on and so forth. So I'd like us to look at a word problem with the average, whatever they have. Okay, let's say average profit. Sparkle Pottery has determined that the cost in dollars of producing X vases is given by, so that's problem 59 on 163, and we are given C of x, the cost function, 4,300 plus 2.1 times x, and the power is 0.6. If the revenue from the sale of x units is given by R of x, which is 65 times x to 0.9, find the rate, which is the derivative, at which the average profit function per unit is changing when 50 units are produced and sold. So first we are asked to create the average profit. So the average profit is the profit, which is revenue minus cost, 65 times x to 0.9 minus 4,300 minus 2.1 times x to 0.6 divided by x. This is the new function that we just talked about. Profit, revenue minus cost, divided by the number of units. The profit is only the top. The average profit is the profit divided by the number of units. Now, they want us to find P of x over x prime, the derivative, when x equals 50. So let's read the problem one more time and understand the concepts and what it's asking. We have the cost function, we have the revenue function. Now the question, find the rate, which is the derivative, at which the average profit. So the rate, the derivative of the average profit is changing when x equals 50. I cannot determine the average rate of change when x is 50 if I don't have the function. I don't have the function yet. I only have the p of x over x, which is the average profit, but I don't have the derivative of this function yet. Once I determine the derivative of this function, I would plug in 50 for x, and I'm done. But as I kindly ask my students always, do not jump ahead. Look at this. This is a terrible function to differentiate. I am not going to differentiate this function as is. I am going to simplify it. First, how will I simplify it? Let me refresh our memory on a particular procedure or steps. Remember, a divided by b plus c divided by b, since they have the same denominator, all you have to write is this. But you can go back and forth. If I have this, I can write this. If I have this, I can split it into two fractions or more, depending on how many terms I have at the top. So if I have two or more fractions and they have the same denominator, I will write this. If I have this, I can go back to the left-hand side. And this is what I'm going to do. I'm going to apply this little trick, if you want. I'm going to only because the denominator is one term. If I have something like this, the method I'm showing right now, it's not going to work. There is no point in separating. You're not going to be able to simplify. But because the denominator is just one term, I can do that. I can separate the fraction, in this case, into 1, 2, 3 fractions based on the number of terms in the numerator. So I'm going to write it again. So p of x divided by x equals 65 times x to 0.9 divided by x minus 4,300 divided by x minus 2.1 times x to 0.6 divided by x. Why am I doing this? I am preparing this function for differentiating it. I don't want to differentiate this. It is easier if I simplify first. I haven't done that yet. I only separated the big fraction into 3 fractions. 65. What do we do with the exponents when we divide two exponential notations with the same base?
You subtract them.
Subtract the powers. Excellent, thank you. From the power of the numerator, I have to subtract the power of the denominator. And I get 0.9 minus 1 is negative 0.1. Minus. Is there another way of writing 1 over x without fractions?
$4,300 to the negative exponent.
So remember, 4,300 is multiplied by 1 over x. It's the same thing. So how do I
So it
write?
would be negative 1 over 2.
So this is x to negative 1. So let's write let's write this rule again. A to negative n equals 1 over a to the nth power. So I have 1 over x to power 1. So this will be x to negative 1. Then I reach the third fraction, negative 2.1 times. The same thing. From power 0.6, I subtract 1, so I have x to negative 0.4. Although it's still ugly, this is more human to differentiate than this. And then simplify. Okay, so now I'm ready to differentiate it. So now I have p of x over x, everything prime. I bring down the power. 65 times negative 0.1 is negative 6.5 times x to negative 0.1 minus 1, which is negative 1.1. So I'm applying the power rule. I bring down this power, I multiply by 65, and then I subtract 1 from the power. Negative 0.1 minus 1 is negative 1.1. I bring down the power, so it's positive now, 4,300 times x to negative 1 minus 1, which is negative 2. Okay, now I bring down the power, so it becomes positive again. So I get, 84, and I have 2 decimal digits, so 0.84 times x to negative 0.4 minus 1, which is negative 1.4. Ah, wasn't a nice situation. Not too friendly, I would say. Okay, now finally, I can evaluate this function when x is 50. So p of x over x prime evaluated as x equals 50 equals. I will put this whole thing in the calculator and plug 50 in. So I'm going to share my screen and plug it in. Okay. I prefer putting it in the function, but that's me. So negative 6.5, because I want to see it. It's better if I see it like that, but it's up to you. The caret and power, negative 1.1. Also, sometimes another question follows. So it's easier if the function is already in there. Maybe they ask me to evaluate for something else, and it's already in there. Power, negative 2, close, and then plus 0.84. Oh, I always forget that. Bring it down. So 4,300 times x to negative 2, and then plus 0.84 times x to power negative 1.4. Okay, I think everything is fine. I'm looking at it. I think I entered everything correctly. I just want to double check that I have negative, I think I do have negative 6.5 in there. Yes, I do. Now second and table, plug in 50, done. So the rate is 1.64. $1.64 per unit. So it's increasing. So the rate of change of the average profit function when x is 50, 60 are produced and sold, is this, and this predicts the rate of change of the average profit when we manufacture the 51st unit. Any questions on this? Any questions?
Could we try another problem like
Yes, absolutely. All we had to do was create the function differentiate the function, and plug in. Okay, what about population growth? Is that okay? So the population P in thousands of the town of Coyote Wells is given by, so we have the function, I'm going to copy it. So that's my page 6. P of t, so this is 61. P of t equals 75 plus 500t over 2t squared plus 9. T is time in years, and P is in thousands. Population. And X is time in years. Okay. They are also graphing it for us. Fine, wonderful. Find the growth rate. What am I asked to find? Find the growth rate of this function. What am I asked to find?
Derivative.
Excellent, thank you so much. So P prime of t, 75 prime is 0. But now I have to use the quotient rule on this. 2t squared plus 9, everything squared. 500, I want to draw your attention to just this fraction for a moment. This can be rewritten like this, because it's just one term at the top. 2t squared plus 9. So I'm going to leave the 500 in front, so I don't have to carry it over. Stays outside patiently. It's a constant times a function. So let me write this rule. A constant times a function prime is the constant times the function prime. So I leave the constant in front only because there is nothing else that follows. If I have here plus t squared, I cannot do that. But I try to simplify a little bit. Is it wrong to keep the 500 in there? No, it's not. Okay, perfect. So the top prime is just 1. So then I have 2t squared plus 9 minus, remember the rule, the top times the denominator prime, which is 4t. One more time. I left 500 outside. I differentiate the top, I get 1 times the denominator minus the numerator times the denominator prime. Now I jump over this, follow the triangle, 500 in front, 2t squared plus 9 minus 4t squared divided by 2t squared plus 9, everything squared. The 2t squared minus 4t squared will be negative 2t squared, negative 2t squared plus 9 over this. Do not touch the denominator. It would be a terrible mistake to try anything. So this is part A. Find the growth rate. Then they want us to do this. Find the population after 2 years, find the growth rate after 2 years, find the population after 12 years, find the growth rate after 12 years. So, with a graphing calculator, I'll eliminate everything that I have, I clear, and I will enter the function itself, which was 75 plus the numerator 500 is just one term. Otherwise, I would have put it in in parentheses, but there is no need because it's only one term, and plus 9. So this is the function itself, p of t, 75 plus 500t divided by 2t squared plus 9. Now I have to put the derivative in, which is 500. I have no choice, but I have to put parentheses now. Negative 2t squared plus 9, close, divide by, open again, 2t squared, plus 9, close, but squared. All I have to do now, I have the functions. The first one is the function, the second one is the derivative, second and table, and they want us 2, and they want us 12. That's it. I have both answers at the same time. So what do I write? I write that P of 2 equals 133.82. Its population. I know that they probably want us to write 134, but when it comes to population, 0.82 of a person does not make a person.
Can you switch back to your screen, please?
I'm sorry?
Can you switch back to your screen?
Yes, I just want to copy them.
Oh.
Yes. This time I did not forget. And P of 12 is 95.2. And P prime of 2. P prime of 2. I meant to write P prime of 2. And then P prime of 12, and I'll go back to my screen. So P prime of 2, what was it? Let's go to the right. 1.73. And P prime of 12 is, look at that, negative 1.58. This is in dollar, this is, I was still thinking of dollars per unit. So this is people. And this is the thousands, actually. Oh, okay. So either write thousands or better, P of 2, 133,820 people. And P of 12, 95,200 people. Okay, so let's discuss this. It was indeed 2 and 12, right? I assume that I remember correctly. Yes, it was 2 and 12. So as you see, when the time is 2 years, you see there is a peak. At 12 years, the function has decreased already from this number to roughly 95,000 that we just determined. So after 2 years, this is the population. After 12 years, this is the population. The rate of change at 2 is a positive number. Number of people per year in thousands. So thousands people per year. The same thing here, the same measurement unit. So this is decreasing and this is increasing. Any questions? Okay, final rule, I promise, for now anyway. Final rule is in 1.7, the chain rule. This is the top rule in differentiating. What does it mean, first of all? Why the chain? Well, if I have, let's say, f of x equals x squared, I know you're going to say that f prime of x is 2x. There is nothing else in there. But actually, the correct rule is times x prime. But it happens that x prime is, can anyone tell us the derivative of x? When I differentiate x, what do I get?
1.
Exactly. So that is the reason why we don't write this. There is no need, because something called the inner function, when I differentiate it, is 1. So what happens if I have, let's say, f of x equals x squared plus 1 to the 12th power? I'm not going to take this to the 12th power. It will take me, if I use a formula, it will not take me that long, but if I just FOIL, it will take me 20 minutes. How do I differentiate something like this? Very simple. The idea is the same with differentiating x to the 12th power. I will get 12 times x to the 11th times the inner function prime. But it happens that this is 1. So this is something called inner. This power is the outer. What does that mean? Again, let me explain again the inner and the outer. If I am asked to evaluate this function at 1, I can't take to the 12th power. I have to perform this operation first. This is the inner. And when I'm done, I will apply the outer. I will take this answer and take it to the 12th power. So in other words, this is the first priority, and this is the second priority. So f of 1 would be 1 plus 1, which is 2. When I'm done with that, then I raise to the 12th power, which is the second function in line. So this is considered the inner, because I have to evaluate it first. And this is considered the outer, because it will wait its turn while this is done. So how do I differentiate? The rule is the following. So f prime of x equals, I differentiate the power first. 12 times the inner function to the 11th power times the inner function prime, which is 2x. So when I have a function, not just plain x, taken to a power, I differentiate in the same way. But this time, this is not x. This is x squared plus 1. And when I differentiate it, I don't get 1. Therefore, I have to have it in the problem.